Good morning, everyone. It's 10:10, so I'm going to get started. Welcome to this session and welcome to week 5, April 20th. And I hope you've had a good weekend. Happy Monday to everyone. We have started talking about reducibility. And if I was to go by genuinely the sort of title I was giving to these lectures, this would have been Reducibility Part 4. Instead, I decided to go with the abbreviated version of it, which is what we will be talking about today, mapping reducibility, a special kind of reducibility. And so the goal today is to wrap up this discussion on reducibility that we started last week. We've had 3, and this will be the last one. And it, as I mentioned last time, is a nice connection to an upcoming topic. And so I welcome everyone again, and we will get started. And we'll get right down to business today so that we would finish this topic. And I have one other thing that I would like to address today. But let me, while people come in, have our warm-up question. This one is going to be very tightly coupled with our own course. And so if you were to sit down and try to remember kind of machines we have been looking at in this course, and there were quite a number of them. So we started off with NFAs, finite automata, non-deterministic, and well, deterministic is actually how we started DFAs. And then we moved on to NFAs. And then later on came something called push-down automata. And then there were some versions of them that have got some restrictions to them and things like that. And then came context-free grammars. And because of that, or rather after spring break, we started looking at Turing machines. So we had that finite automata, deterministic, non-deterministic, push-down automata, Turing machines, and a whole bunch of variations of them. In fact, the very last thing we saw last time was about a special kind of Turing machine that have got restricted memory, and they were called linear bounded automata. So there is quite a number of machines we have seen so far. If you were to pick a favorite, and it doesn't matter how you pick a favorite, which one will be your favorite? This will be the kind of thing that you would say, I like them, they look cool, or they have nice, when I draw them, I like them, or I have understood them, whatever it is that makes it your favorite, and you are going to make a poster and put it in your bedroom. Which one of these machines would it be? So among the machines we have looked so far in this course, what is your favorite? Not a movie, not a game this time. We are looking at machines, computation machines, or models that we have been looking at in this course, and you have to pick your favorite. So go ahead and participate and tell me what your favorite automaton is, that your favorite machine is in terms of understanding theory of computation. So automata in formal language is how this course is called. So we saw a number of them, and so you may remember some of them would come to mind when you start to think about this one. All right, so part 4 of reducibility, in particular mapping reducibility, is what we'll be talking about today. Let me begin by having to just have us look ahead in where we are, what is left, and also just take a peek at back. We are in week 5. Today is April 20th, and we have completed 4 weeks since we started with doing things online. And so in those 4 weeks, what we looked at was Turing machines, chapter 3 of the book, decidability, chapter 4 of the book, reducibility, chapter 5 of the book, which is the topic we are doing also now. And so we have 2 weeks of lecture left. Week 5 is where we are. Week 6 will be the week after that, and finals week is week 7. What I plan to do this week is finish up the topic on reducibility today, and have 2 of the remaining lectures in this week be on things that would be complexity theory part. And this is not the part that is a heavy weight on our course, but I would like you to get a flavor of it. And so I'll talk about complexity classes at a very high level and introduce some of those notions. And on Friday, I'll talk about intractability. And you will see the connection why the mapping reducibility topic we are doing today has got that connection, and why I call this one has to do as a tie for an upcoming topic. So that will be the subject of this week. And we will have our homework 7 to on Friday. So that's a reminder. And that will be the day when the last homework will be out, and it will be due a week later. That is week 5. That's the week we are in. Next week, I would like it to be a week of review and wrap up, in general speaking. And so we will use Monday's topic to wrap up the course, see some way of reviewing things, and then we will devote Wednesday's lecture to review for final, And Friday, as we have agreed, we will do the final exam just like we did for midterm 2 take home. And that will be the day when it will be released. It will be out. And so the review for final in terms of topics and things like that that you need, especially for places where you have questions and things like that, will be done on a Wednesday, but the exam itself will be introduced May 1st. The very last day of lecture will be where the final will be out. We will decide whether it's going to be 48 hours. That's what my current thinking is, or it will be due on Monday, or we will find if there is a better way to do it. The final exam is not made yet, but I have a plan for how to go about it. And so that will be the day when it will be introduced, and we will talk at another point where the final form will be. So we have 2 weeks to go. This week is wrap up on reducibility and introduce complexity classes and intractability. Next week is, in one word, a week of review. And the last lecture will be devoted to introducing the final exam, which will be taken away. Week 7, you are going to be doing your finals, both in this course and in other courses. Ours would come on a day we will decide, but most likely the very first Monday. So this is what we are looking ahead. And when we look back, we have completed 4 weeks where we have looked at Turing machines, decidability, and reducibility. So this is what I want to start off today, but there is one other thing I would like to do. And that thing has to do with homework 7. Most of you, I am sure, have looked at the problems. Some of you might have solved all of them or portion of them. And here is how they look like. This is a slide from some time back, the first time it was out. In fact, it was a week ago, I guess. It was on a Wednesday. And that this one was, it's not a full week, but some 4 or 5 days ago. And so I've gone through this and we have looked at the problems that this homework covers, but there's a peculiar kind of problem that I thought would be good to give you a hint on. And that problem is problem 2. Before I give you a hint on it, let me back up and try to get the genesis of this one right. This came up in a discussion we had about Turing machines and the role, the Turing Church thesis, the role the definition of an algorithm played in answering a big question that was posed in 1900 by Hilbert. And it got problems, and it got 23 of them. And the 10th problem had to do with something that had to do with polynomials and their solutions being integral. And we know now, in 1936, it was proved that this problem is undecidable. Why? Because we have a tool for doing it. And that tool is what the undecidability discussion started off, and we talked quite a number of things around it, okay? And that problem is generally undecidable. That's how the diagonalization technique, that's how counters work and so on was introduced. In that case, I say there is a special case of Hilbert's 10th problem that is decidable, and that is when the polynomial is of a single variable. So the single variable case became when we're asking whether the polynomial has integral solution root, and so a root is something that will be equated to 0, and that one, when that value is integer, we call it integral. When that polynomial is of single variable, the problem is decidable. In every other case, it's undecidable. Every other of these cases, for those of you who are curious, are topics of dissertations. People would write theses around just the second case, when the polynomial has got 2 variables and so on and so on. But generally, we know that that problem is undecidable. The reason that it is decidable when the polynomial is of single variable is because we can say something about what the roots, so we can bound certain things, so we can search in a manner that makes the Turing machine hold, basically, right? So there is a search space that is limited to us. And so in that discussion, in that lecture that covered that topic, I say this case, the book has formulated this as a problem, is a problem that you should not have too much trouble to show. And I wanted you to go about it and look at it. And so that was why that problem was included. And so it has got a very different flavor compared to the other kinds of problems you would see in this course. This course has got language, you've got decision, you've got Turing machines to build, you've got decidability or undecidability to show. There is something about strings, something about that flavor. So you have now, by now, you're good experts in this course in a way, to some degree, and therefore you would notice the moment this problem is posed to you and to look at it and then say, it looks very different from everything else. So the problem, when it is the way it is formulated in the book, and also you're given in problem 2 in homework 7, reads like this, the 20 points at the back. So you've got a polynomial now of a single variable, and that's x. So you've got these coefficients that are associated with each of these terms, depending on how the degree of that, that variable is, to the power of n to the power of n minus 1, and so on. So you've got this expression, that's a polynomial of a single variable, and it says it has got a root at x is equal to x0, and then there is a definition for a certain coefficient among these ones, and we call the one that has got the largest value Cmax, and you are supposed to show this inequality. This is the reason why the search will be in a limited space, and therefore you can decide the reason that that problem becomes decidable. And so I can appreciate if, and I told you, this is a math problem, it's very different, and the way you see it now, you don't see anywhere about Hilbert. In fact, you don't see anywhere about decidable, and so you don't see anywhere where the Turing machine would show up, and so you may get a little bit puzzled. And so I thought I would give you a hint, and the hint is given there. But let me also try to maybe also give you a reason for why sometimes some of these proofs we see in the mathematical computation theory course like this one, where you have, sometimes to dig up a tool somewhere from some other courses you've taken or some other knowledge you have, and where you formally argue for something. Those are what the proofs are. And so the kind of proofs we have had so far heavily relied on language theory and things like computability and things, that you have material for as the course progressed. And so there wasn't a whole lot of time when we needed to go back and get some other knowledge from somewhere else, except for a couple of cases. I remember there was a time when we had to show the pumping lemma, for example, and so there was some fundamental things that we know from math that came handy to bound things and so on. So this has got a little bit of a flavor of that kind. So there is a few hints here. And once you've got these hints, it should be straightforward or relatively straightforward for you. But I still would like you to formally be able to answer a question like this and show that proof. Okay, so the first thing to note is that you are told x sub 0 is a root. Another way of saying it, that would be if you plug in x0 into that expression, it would equate to 0. So that would be your starting point. And so when you see this thing that you are asked to show, it tries to kind of find something that would help, bound what this root is, what the x0 is. But if you see the other ones, you probably would get an idea for where this one is headed. So the first thing that you would want to do is separate the first term of this one, Cn x to the power of n, and from the rest of it. Once this is equal to 0, then you can move the other thing to the other side of the inequality, and so you've got something that would be equal to minus something else, right? And then that's where the use of absolute values would come, because now you have something on the left that involves C1 x to the power of n, and some other thing, a whole bunch of things added up together that will be a minus. And so you can make these ones equal if you take the absolute values of both of these sides. Okay, so that's bullet point number 3. And then it says, I have given almost 3 now an inequality that would be helpful. So you're bounding. So the thing is started with equality, and this is a standard practice when you show things like this. In fact, you will see more of these things as you progress in your course, and maybe take algorithms course or some other things that you would do. You would want to bound things. That's probably more important than exact ones. In fact, computer science is very less known for having to have equalities. It's bounding. We'll actually get to that sort of thinking later on in this week. But you want to bound those. So if you have 2 terms that are added, then it should be obvious. This should be obvious for you to see. If you were to break up these ones, then the absolute value of this sum, the a and b of one or both of them could be negative here, would be less than or equal to the absolute value of the first term plus absolute value of the second. This could be extended to many terms, and so you need to see and use that in the expression you got. And then you will have to get rid of all of these xn to the minus n and so on. And one other hint I have given you is, if you were to write, now compare these terms, x to the power of n, and you compare it to xn minus 1, what could you say? And if you have now given a name for the coefficient that's the biggest out of this one, so you can have even more bounding using that. And then you could, it should be obvious now what I'm trying to tell you, otherwise I would have spelled out the exact solution. So you can try to bound xn with, in terms of, you can write these other terms in terms of xn by bounding them again, and then this would follow, just some manipulation. So I think with this idea, with this hint, you should be able to do problem 2. The other problems are problems that are of the natural type, the kind of thing that we were used to in doing in these ones. And so I don't think I need to give you a hint, but if you have questions, of course, you should be reach out to James, and you've got a couple of his hours this week, and get help on things like on how to go about. But I think they should be okay, except for the Magic the Gathering problem, where you would be on your own and have fun trying to come up with some concise answer for the couple of questions that that problem asks you. Okay, this was the hint I wanted to give you, and I want to get started with what we would like to do today. But before I do that, let me see if there is anybody who has got any questions for me. Anybody has got any questions for me? You should remember to unmute yourself and ask if you have questions, but this is, I'm going to get started with what we would like to do today. Okay, was the hint on problem 2 helpful? Okay, okay. Okay, I'm going to get started with the topic for the day. And we are going to be talking about mapping reducibility. And reducibility is a topic we have started on last week, and we've had 3 things covered. And so we know what the basic idea is. And we are going to just make it a lot more, or a little bit more formal now for a particular purpose we have. It's just a coincidence that we have these words map and reduce, and I never actually paid attention to that until James pointed it out today. For those of you who are in high performance computing, or things that you probably have, you don't have to be there, but you probably have heard map, reduce. That is a paradigm, a way to compute things when you are on the cloud, and so you have to map and you have to reduce. Has nothing to do with this, but we have made use of a powerful technique called reducibility to show problems when they are undecidable. And we grew a list of undecidable problems out of a basic one that Cantor proved to be, or we proved through diagonalization, ATM, the acceptance problem of a Turing machine. We showed that the hard way by using diagonalization, and then we said we can reduce from that problem to a problem we look for, and if we can do that, and we have a Turing machine that did it, we call that method reducibility, and therefore we show this second problem is also reducible. And we're going to make, there was quite something that we did in that reduction. We produced the Turing machine that needed to do that one, but we are going to make it even more formal, and that is where this term, now the reducibility, has been qualified, and that one has been called mapping. And there is a number of different ways in which this could be formalized, and we're going to treat one of them, but we do this in a more refined way for a couple of reasons. One of the reasons is because we want to, we have been using it for showing things that are undecidable, but we want to show it for things that are also not Turing recognizable. One of the goals I have for today is to actually, by having this being a little bit more nuanced, more refined, by defining it in this way, we become able to show things like not Turing recognizable language. The other thing is in complexity theory. This is the connection. This is the connection why we will have the lectures that we will have now on Wednesday and Friday are related to mapping reducibility. And you will see why that is the case. And so among the very, or not very many, but among the many, at least several ways in which reducibility could be more formalized, we will choose something called mapping reducibility. And so the basic idea is the following. To be able to reduce problem A to problem B using a particular kind of reduction called mapping reducibility means that we are going to have a computable function. This is the place where we didn't bother to worry too much about whether that one was computable, whether that reduction was a function. All we did so far in using reducibility in a general way was to come up with a Turing machine that does that reduction. And we will get a couple examples today where we will see, go back, look at what we did with reducibility and see if that one would lend itself to being a mapping reducibility or if it needs something more. So we're going to be looking at a computable function that exists to convert instances of problem A to instances of problem B. The reason it's called mapping reducibility, when we formally define it, it will be clear, but you see the word mapping. That means I'm able to convert every instance of this problem A, from which I started, to every instance of problem B. And so there is a distinction between talking about the problem in general and talking about every instance of that problem and every instance of this other problem that we are reducing it to in particular. And so when we have that mapping, then we have that function, then we are going to be able to call this thing mapping reducibility. So the idea carries over exactly the same way as we have done last week. We have a starting problem, we have a problem that we are reducing it to, and we call this thing a reduction. And if this conversion is done using a computable function, then we will call that reducibility a mapping reducibility. Okay, so let's formally define this. By formally define this, I mean by beginning to define what computable functions are. So we're going to do this thing in two steps. So the mapping reducibility will be defined in the next slide. And one of the components we needed for it was the existence of computable functions. So let's first go define what computable functions are. So the idea now, we will still be working with our Turing machines. The idea now will be to talk about a function in which we have the input of the Turing machine start us with a string, and then it is going to produce, or the Turing machine is going to end up with something on the input tape now that would take from whatever input it was to whatever the function of this function that we are defining is going to give us. So a function f that takes from a given alphabet in the same alphabet is a computable function if some Turing machine M exists, so that on every input W, it holds on with just f of W on its tape. So it starts with W on its tape, and it holds with just f of W on its tape. So all that the Turing machine has done is compute that function, basically. So it started with W and ended up with f of W. So we can come up now. So bear with me with the technical things here. So we could call, for example, the functions that we know in arithmetic, the sum of two numbers, the product of two numbers, the difference of two numbers, that type of thing is a computable function, because I can take the encoding of the two numbers that I'm adding and give me the sum, the tape that would give me the sum. And so that will be an example of an arithmetic operation. Another example of a computable function will be something that would turn the transformation of a machine description and give me another machine description. For example, if I have a function f that takes input W and returns a description of a Turing machine, n bar, n prime, whenever the input was the description of the machine M, now I have an encoding of another machine. And that will be called M prime. And that function that turns one description of the machine to another description of a machine could be called a computable function. For example, we had seen an example of this kind when we were looking at a machine that we wanted to prevent it from going off of the left end of the input tape. We needed that to prevent something from happening, for example, when we were working with CptS. And so that function that required us to introduce another state or some other mechanisms or introduce a symbol to indicate that we have come to an end, that type of function is also a computable function, but it is not an arithmetic function, obviously. It had to do with transformation of a description of a machine. So these type of functions are called computable functions. We've got a way to start the input tape with string, and by the time the Turing machine is done, what we have on the tape is a function of that input string that we started with. Such things are called computable functions. And we will call a mapping reducible. This is the formal definition. And just like what we have been doing so far, we're going to turn these problems in terms of language. We can also talk about other types of problems, but for the purpose of the discussion I have now, we can think of language, membership in a language, and we decide whether it is decidable or not decidable, Turing recognizable or not Turing recognizable In other words, our problem is now formed in the form of a language. So we'll start with that. We have a language A, we call it mapping reducible to a language B, just like what we have called so far, that we were able to reduce one problem to another one. We will start with a language A, and we will reduce it to language B using a particular kind of reduction. And that reduction has got a notation in what we do here in the book. And that notation is this less than or equal to with an M, and the M there is for mapping. So written as A is mapping reducible to B if there is a computable function that takes from input to output, such that wherever we have A, the W member of A is the same thing as saying f of W is member of B. So that means now we have a one-to-one mapping. Everything that we could say in terms of treating input strings in A, now we can take, once the function has been computed, we can think about mapping in membership in B. So the two are equivalent is what we are saying. So the function, when it is like this, is called a reduction from A to B, and you've got a visual illustration of this one. So the only thing that probably you need to pay attention to now, it will be clearer when we get concrete examples. You may ask me, you've been doing this all along. We've got all those, 8am, we changed it to whole 2am, we had regular, we had all those growing list of things. We were busy. Sometimes we took 2-3 slides to show that we were able to reduce one thing to another. And so what's new? The new thing is here we have defined exactly what that mapping function is, and we show that it is computable. And there were things that we were not that specific, that refined when we were doing things generally in terms of reduction. So this type of reduction is called a mapping reduction because it has got every instance of problem A being reduced to problem B using a function f like this one, and so we explicitly give that function, and so such a reduction is called mapping reducible. So I've got an agenda. I'm going to show examples now, and the examples I will show when reducibility is used for a decidable problem, when mapping reducibility is used for an undecidable problem, for a Turing recognizable problem, and for a Turing non-recognizable problem. When it is decidable, keep in mind everything that you've been doing so far, knowingly or unknowingly, in all of your courses and so on, would belong there. I told you last time, when you have a function and you try to abstract out something and then you write a subroutine, you're using it. What you're doing is you reduced something that was computable into something else, and you used the computation of that thing that you have come up now to solve the original problem. That's basically what it is. And the undecidable problem is showing that one is a matter of argument. I'm going to start with something that I cannot decide. It's undecidable. I reduce it to another problem. And because I have done this successfully, this time using mapping reducibility, then I'm going to conclude that the newcomer is undecidable also because of this existence. And therefore, it's not about solving the original problem. It is about showing the new problem is undecidable. Exact same way, we can argue about non-recognizability and recognizability of certain language. The last 2 points are a little bit important now, extra important now, because we are going to be using this refined notion of mapping reducibility to be even more nuanced. So that's where they would come. So bear with me, we'll see these 4 examples. We'll start with decidable problems. So we'll start the theorem, we'll state the theorem like this, and we'll give a proof. This one is among the easiest. So if I've got language A, mapping reducible to mapping B, if B is decidable, then A is also decidable because I can use the solution for B to solve A. The formal proof for this one looks like this. And I'm going to spend a little bit of time to try to explain this one because we're going to use this to show some other thing that is very similar to it. And so when that time comes, I will be briefer. So this one, we've done this before when we were not necessarily thinking about mapping reducibility, but reducibility in general. And so the idea here will be to actually state it in the form of the computable function f. And so that's what this proof is doing. So we've got M be a decider for B, the one that we are reducing into, and we will call the function that reduces from A to B, we'll call it f. And so we're going to describe a decider for N, for a decider N for A, which is what we are going to show because we know that B is decidable, and the machine for it, we have called it M. So we're going to exhibit, we're going to give the decider N for the original language or for language A in the following manner. So N is going to run on input W, and so it's going to compute that reducible mapping from A to B. It's going to compute f of w, and then the second step will be to run m on the input f of w. Now we have a decider for B, we know, and so we're going to run that m, which is a decider for B, because now we have computed this function, and we will output whatever m outputs. If it accepts, we'll accept. If it rejects, we'll reject, and therefore we have. So what is it that we've done that we didn't know from before? Well, all we have done now is explicitly stated what that function would be, and then so we have written it. So clearly, if w is in A, then f of w is in B, because the f is a reduction from A to B, and therefore m accepts f of w whenever w is in A, and therefore it is deciding. Therefore, this n, the machine that we just constructed, works as desired. When I revisit this one to show something else later on, I will be briefer, but this one should be so obvious and very easy for you to follow along. Now let's talk about undecidable. And so we could write almost the same statement. I'm going to go back and show you this statement that's in green now is going to be used almost exactly, except now we are going to be using it. If B is decidable, then A is decidable was the conclusion. Get the logic, you know this from before. So if I know B is decidable, then A is decidable. So it goes to the left or backwards. Now, when it is undecidable, I'm starting with the problem that I know is undecidable. So if A is undecidable, then B is undecidable also. Why? Because if it were not, then I would have been able to decide A also. And so this time we have seen this all week long last week, except now that the reduction is mapping reducible. So the reduction from ATM to halt that we saw undecidable last time could be used as an example here. What we will do now is, at that time, we didn't care to show the function f, but otherwise the argument was all there in place. And so I wrote again what we were doing there. And so if you see the proof that we will see now and the proof that we saw last time to reduce ATM to whole TM, they are very, very, very similar. So there, what we are going to do now is make that computable function explicitly stated, and it will take the input of the form m and description of w, and it returns at the output the description of m modified, where a membership MW is in the ATM will be true only if and only if the new machine M prime and W prime is in halt. And so the function that does this, the computation, will call it big F. So the reduction is a small function f, and we'll call the Turing machine. The machine that will do this will call it big F. And so it takes on input MW. It will construct a new machine. And you may remember how this idea about halting was doing. And so it will run on the new machine on any input X, run M on X. If it accepts, accept. If it rejects, it will enter a loop. That was how the fact that we are not able to know whether the machine is going to halt was terminated. So this argument and what we had before are exact parallels of one another. The only thing that we have done now is call the computation around M prime to be called the function f, and so then we will output the result of the new machine on this input, and that will be what our f would be. So we have now seen an example where the computation that was involved in showing the reduction when things were not in a mapping reducible fashion mapped almost as is into a case where it is mapping reducible also. We will see example where that is not the case. For that one to see, we'll take another example. So we saw one example where we say it's not a big deal. All we have cared to do was to take this reduction that you have been showing us before, and now you are showing us how to make a mapping reducible by exactly showing the function to be used. And that worked for halt to ATM. Here is another example. We spent quite some time talking about ETM. That was a language that has got to do with emptiness. And so that was undecidable. And we reduced it from ATM, and we showed how that one was. If you remember, I have wrote this slide exactly the way it was from the lecture that was given on April 30th. And so it had got a little bit things on the slide, on the title, but otherwise it's exactly the same slide. But what we arrived there was we did something and that idea was not a good idea. And so we had to modify another thing. And this was how the description looked like. And you don't necessarily need to remember everything that was said at that point, but this emptiness was shown in a way that was indirect. And so there was this machine that we constructed, we called it M1 as one of the steps, and it was working and rejecting everything except W. And when it is W, it was running M on input W, and it would accept if it does. That was the modified version. And we used that one as a stepping stone for having to come with the machine that would simulate. This was part of the thing that was needed in the modification. But what we ended up doing was doing the opposite of what this machine was doing. So if R accepts, we reject. If R rejects, we would accept is how we did when R is a machine that's run on this modified machine, M1. Now, if you were following at that time and you remember the argument, great. If not, then you have got a chance now to see what this one was doing. But there is one specific point I wanted to point out. This one, unlike the previous case where we saw a reduction from ATM to halt, worked out seamlessly into turning it into mapping reducibility because the function was easy to see there. This one does not, and you will see the reason. This one was a recollection, and so all it did was reduction worked out fine, but it had got a detail. And so this is a comment on what that reducibility lacked. So from this original reduction, which is what I showed you in the slide now, we may easily construct now a function that we could call a mapping reducibility, the function f, that takes MW, the description of the machine and the input string, and produces an output like M1 would do. But M accepts W, I should have done the W there, read, so just you see it, but I forgot to make it a read, if and only if the language of M1 is not empty. So F is a mapping reduction from ATM to ATM to ETM complement, not ETM itself. And so it was doing the opposite. So if R accepts, it rejects. If R rejects, it accepts. And so the reduction is there, but it was not a reduction to ETM, but rather to ETM complement. But for the purpose we had at that time, which is to show that whether this problem was undecidable, we were fine. Because this issue about decidability in the reducibility we had at that time didn't make a difference, because if we could decide a language, we could also decide this undecidability by changing what the Turing machine would do. It would reject if it accepts, it would accept if it rejects. But if we are going to do a mapping reducibility, this reduction will not work. In fact, we cannot. There is a problem in the book. I'm not going to ask you to do it in your homeworks, trust me, but you can show that such a reduction doesn't exist. So that means the mapping reducibility now is sensitive to complementation, whereas reducibility in general was not. Perfect example for why the nuance is needed. A good reason why we're spending the lecture we're having today. So this one now brings us to caring about having to see when mapping reducibility is used for showing things around, just like we did for Turing decidable and undecidable is so far what we're seeing. We could also use it for Turing recognizable problems and Turing unrecognizable problems. So the real motivation why that mapping reducibility was sensitive to complementation will become clear now when we look at Turing recognizable and Turing co-recognizable, which you remember from last time. So let me begin by having to state this theorem again. The equivalent of the mapping reducibility used in deciding language that are decidable, let's use them for showing things that are around Turing recognizable. So if I have language A and language B, and language A is mapping reducible to language B, and language B is Turing recognizable, then A is also Turing recognizable. This is exact same parallel, except now we are calling things that we call decidable Turing recognizable. And this statement would hold with the same exact proof we saw when it was decidable, just by replacing every decider with a recognizer. And there are two incidents. We've got M, the decider for M, what he used to be, and we'll call it a recognizer for B. N, the one that we're constructing, used to be a decider for A, now will be a recognizer for A. Other than that, the proof works exactly the same way. And so we have a theorem that we can prove in 15 seconds because we have seen how to do this when it was about Turing decidable ones. So we did check. If you are following with me now, I told you that we will talk about this mapping reducibility and show it for decidable, undecidable, Turing recognizable, and Turing unrecognizable or non-recognizable. I don't think it's an English word, unrecognizable. Non-recognizable is probably the right word. So we've seen 3, and we're going to see the 4th one now. But before I do that, let's do a corollary. Well, I'm exactly doing that. So it will be a corollary to the theorem we just saw. So if B is Turing recognizable, then A is Turing recognizable. If A, now we go to the left, if A is not Turing recognizable, then B is not Turing recognizable. Why? Because if it were not, then I would have used the solution for B to solve A. But I know that A is not Turing recognizable, and therefore B is not Turing recognizable. So this is follow-up, a theorem that would follow from the theorem we just saw. But we've got a new one now. Now this is the place where I come to my 4th, to the place where I will use mapping reducibility to show something that is not Turing recognizable in a new way. And we're going to get a concrete example. And that concrete example of ours is EQ. Now this handy shorthand notations for all languages would require a little bit of remembering what we've been doing, but I trust that you have very good memory. And so you remember what EQ was. So ETM was the language where it was about emptiness. EQ was the language where we have 2 languages, L1 and L2 given, and we are going to decide whether they are equal. That was what EQTM was. And we remember that was undecidable, but we now know, we'll show now, this one is neither Turing recognizable nor co-Turing recognizable. It's not either of them. So EQ, so if I break this one up into 2, it would say EQTM is not Turing recognizable. And then the other part would be EQTM complement is not Turing recognizable. That's what this theorem would mean. And that's what we're going to show now with our newfound knowledge with mapping reducibility. So get ready for a slide that has got 2 contents in it, because it will have to show 2 parts. So don't get bothered too much by having too many things, but I would rather have you both of them at the same time. So the first one will show, the top box will show EQTM is not Turing recognizable, and the bottom part will show EQTM is not Turing recognizable. For the purpose we have now, forget the bottom part and let's look at what we have on the EQTM is not recognizable part. And so what are we going to do? We are going to reduce from something that we know, and that something we know will be ATM, and we're going to reduce it to EQTM, and we will do that through a function that is mapping reducible, and that will function, we'll call it F. And so that's what you see there. So F is going to take M and W, the encoding of it, where M is a Turing machine and W is a string, and it is going to construct 2 machines, M1 and M2, that will do the following things. M1 will reject everything. On any input, it would reject. M2, remember what EQTM is doing, it's talking about their equivalence. M2 is going to take an input and it is going to run M on W, and it would accept if it accepts. Now, M1 and M2 clearly are not equivalent, and therefore this reduction would work, and it would output what M1 and M2 would do. And so you can do the converse and show that the converse will not be true. That means they are not equivalent, and therefore we have now a way to reduce ATM, the decision problem, into a problem that would be talking about the equivalence of 2 machines, and this one is not recognizable. And the mapping that we have done for it, F, does M1 and M2 in the way I have just shown you. The complement part now will do something that's different. And the difference comes, and we will call this function that will reduce, just like what we did from ATM into this one, F, to show that EQTM is not recognizable. To show that its complement is also not Turing recognizable, we are going to produce that mapping reducible function, and we will call this one a G, and it will do almost the same thing as F1 does, except that it will do something different in the first step. In fact, it's not something different, it will be something opposite, because this one is a complement after all. So M1 will take on any input and accept it all the time, whereas M2 would run M on W, and it would accept if it accepts. And so the M1 and M2 now will not be equivalent. In fact, they would not be. And so when we run the output on M1 and M2, we will get a result that will give us the complement of, or the opposite of, whether L1 and M1 and M2 are equivalent. So this proof now has now made it possible for us to show that EQTM is not recognizable, its complement is not recognizable, and for both of these we produced mapping reducible function F and mapping reducible function G that would treat each one of these two. And this is the place where I wanted to stop, and this is the place where I wanted to wrap up the discussion about mapping reducibility. So to recollect, mapping reducibility is a special, a refined type of reducibility where we have to produce a mapping function that would take an input in a language and produce an output, a function f of w that would help us determine every time w is a member of language A, f of w is a member of language B is equivalent. And that reduction is done in a computable fashion using a Turing machine. And when we have that, we will call that reduction mapping reducible. When we don't have that thing upon us to show that function is computable, but generally we're talking about reduction, then we will call it reducible. Reducible took us quite some distance last week and show a long list of problems that are reducible, and mapping reducibility made us see a little more things today, and then we are going to also be using it in complexity theory. So it'll be a very basic thing and an important thing to show about intractability. This is where I want to stop. Let me see if you have any questions for me. Anybody else got any questions? Was everything clear? Okay, take advantage of the office hours. Make sure that you submit as soon as you finish your homework 7. Homework 8 will be out on Friday, and we will get to grading homework 6. And when that is ready,
you had one question in the chat. He was asking, what was the question you asked at the beginning of the class?
The question I asked at the beginning of the class is, what is your favorite automaton? NFA, DFA, push-down automata, Turing machines, or any one of those variations, if you remember to see how they were. So favorite machine. In the course we have seen so far, what is it? What was the question? Okay, and that was the warm-up question for the day. Sorry if it was a boring question, but it's a good one. Okay. All right, if there aren't any questions, we spared a minute or two, which is so wonderful. I will stop here and I will see you on Wednesday.